This is a hit and run econometrics on the Phillips curve, a famous curve in macroeconomic history. Policymakers have long wanted to know what is the relationship between inflation and unemployment, two of the big macro problems that every society might have to face. And A.W. Phillips, an economist who was actually from New Zealand, I believe it was, and did his most important work in Britain, um, had a look at the relationship between inflation and unemployment. And when you look at the ordinary scatter of the dots between inflation and unemployment, you get that kind of relationship. And of course, our first impulse might be, well, let's draw a straight line there, linear relationship. But, macroeconomists have a story about why this shouldn't really be linear. It looks kind of curvy, actually. And what that implies is that even when unemployment gets very high, inflation probably won't go negative. You probably won't actually fall into deflation. So if you want to do an accurate Phillips curve, then you really need to make it curve and not just be a straight line. Now, that's where the power of this approach comes in, and that's where the complication comes in. But first, let's have a look and see whether we're likely to succeed. And if you look at that, oh, wow, how could there possibly be a relationship in that? But if you look more closely at the data, what this suggests is, hey, it looks as if there is really a Phillips curve running through there. And then maybe under different macroeconomic conditions, a Phillips curve running through there, and a Phillips curve running through there, and then maybe a Phillips curve running through there. So maybe what we need is the ability to shift the Phillips curve, and then we'll get a pretty good fit. Well, it turns out, yeah, if you have the ability to shift the Phillips curve and hold other things equal, you can get a pretty good fit, at least for certain points in history. So let's write out the equation of one Phillips curve that has been estimated and see how we would go about this. We would say that inflation in time t is equal to a constant term plus, okay, here's where the magic comes. If we just stick in unemployment right there, we're going to have a linear relationship. It can only ever be a straight line, and therefore it can't fit that curve. What if we put in beta 1 times the reciprocal of unemployment in time t? That is 1 over unemployment. Well, that's going to be a reciprocal transformation, and that thing by itself is going to make it curvy. So we'll transform this from unemployment into the reciprocal of unemployment, plug it in, and then we're good. Now, in order to hold other things equal and in effect shift the Phillips curve, we're going to need the lagged inflation rate. Okay, the lagged inflation rate. The lagged inflation rate, that's going to be the inflation rate from the previous period because of persistence in the inflation series. There's also good reason to believe, here's the beta 3, that the natural rate of unemployment, there it is, natural rate of unemployment in time t, would affect the position of the Phillips curve. And then we would have an error term on the end. So that would be the Phillips curve that we would want to estimate. Now, just for convenience here, I have estimated this Phillips curve in lowly Excel. Let's go see how you would go about doing that. Okay, here we would have a data set, and Excel is especially good here for showing you some of the things that you can do with Excel. Here's an example for you. Here is the lagged inflation, lag P like that, and you see that Excel formula up there that says plus C2? It just says here all you did was take the previous year's value of that inflation variable. See that? You just took the previous year's value, you shifted this down one column, and by the way, I went back and looked up the 1963 value so that I wouldn't have to have a blank spot right there. And now we've got that lagged inflation variable that we can use in there. There's a little inconsistency in the labeling of the data here, but it is what it is. And then creating that reciprocal variable there. That's just 1 over H2. Look at that. That's the reciprocal. So instead of plugging in the unemployment rate of 5.2, we plug in the reciprocal unemployment rate, 0.19. So you see, we can do all our data transformations right here visibly in this Excel worksheet, and then go put in for the data analysis here for the regression, the values of our dependent and independent variable ranges. We can do all that. And when we do, here's what we get. The results, bing, bing. Yeah, the results. Here's what the results look like. I went ahead and made them pretty big there. We get an R squared of 0.63, not super for a time series, adjusted R squared 0.607. There's that whole analysis of variance table leading us to a highly statistically significant f-test. No question there. But then we get an intercept, a garbage collector there. And we find here that there's a lot of importance to that lagged inflation rate there. Inflation is highly persistent. And I want to say a little bit about this reciprocal unemployment thing. In fact, a whole lot about this. But I will just note for you here that the natural rate of unemployment, which, really ought to be important here, has a p-value of 0.13, so it's not quite statistically significant. But it does suggest that other things equal, when the natural rate of unemployment is 1 percentage point higher, then the actual measured unemployment in any given year is 0.55 percentage points higher. But here's the thing we really want to know about this recip U. A president might want to know, hey, if we pump up this economy with, if we stimulate this economy so that the unemployment rate goes down 1 percentage point, are we going to have a big problem with inflation? And if the economic advisors came in and said, well, the effect on the reciprocal of unemployment is 25.45, that doesn't make any sense. The president wants to know about inflation and unemployment, not the reciprocal. Who knows how to interpret the reciprocal? And so that's why we come to this exercise here. I just blew this up so we could have a good look at it. And the number that we are most concerned with is making some sense out of that 25.4599, that, 25.46, whatever it is there. And the problem that's stated here, if the unemployment rate goes down 1 percentage point, what does this model predict will happen to the inflation rate? Well, the first thing I want to note for you up here is that for a nonlinear model, there is no one prediction. Yeah, that's right. The very fact that it is nonlinear means that there won't be any one prediction. It's curvy. And so that means that you get a different prediction up in here than you do down there. It's not a straight line. That is its strength, but it does, make the prediction a little more complicated here. So what we do is to evaluate at means. And I'll show you how we do this. We evaluate at means. To find the effect of unemployment, we start with U bar, the mean of unemployment. And for this sample, I just went out and calculated it. Not hard to do. For this sample, U bar is equal to 5.99. Okay, so here's what we're going to do. We're going to make a little table, and for problems like this, I recommend making this little table. We're going to have U, and then we're going to have recip U, which is equal to 1 over U. And we're going to say for 5.99 at the mean of our sample, which is where we're going to talk about this, the reciprocal of unemployment, and just pull out your calculator, 1 divided by 5.99, there it is, it's 0.1668, like that. We're going to say, what happens if the unemployment rate goes down 1 percentage point? Well, starting at the mean, which is our reference point when we evaluate it means, starting at the mean, that would mean going down to 4.99% unemployment, and then recip U becomes 0.200t. See, this is just math. And so when we do just a little subtraction, how big a gap is it? Well, here the gap is easy to see. That's a gap of 1 percentage point. The corresponding gap in recip U is 0.0334. So you just take this one number and then subtract 0.1668, and you'll find that gap. That's why we're justified in saying when U goes down 1. Okay? Recipu goes up 0.0334. See that? That's what our table just said. When U goes down 1, recipu goes up by 0.0334. And then we note one more thing. The coefficient on recipu is, hey, and we highlighted it just to be able to find it easily again. It's like, 25.46. Okay, so let's consider this chain of events. When U goes down 1, see what happened? Then we draw the little arrow that says recip U goes up 0.3. Let's get the decimal place right there. 0.0334. And so that means that our estimated inflation is going to go up by 25.46 times 0.0334. See that? That beta hat means that if reciprocal unemployment changed one whole unit, then the inflation rate would be there, 25.46% higher. But we're instead looking at only 0.03 of that. And so that number there, 25.6 times 0.0334, just pull out the calculator, that gives us a result of 0.85. And so the answer here is that inflation rises about 0.85 percentage points. Let's just go back through that calculation one more time. We were evaluating it means because there's no one prediction in a nonlinear model. We were taking unemployment down 1 from its mean. That caused recipu to go up 0.0334. And so about 3.3 hundredths of the effect of a full unit change we got by multiplication came out to 0.85. Inflation rises about 0.85 percentage points. Now remember, the thing that made us do this weird calculation, was actually in the power of the approach. It was a nonlinear Phillips curve that we got by using the reciprocal of unemployment as this variable. We could always keep it linear, but if we did, we wouldn't get nearly as good an estimate. And that is a hit and run on the Phillips curve.